Hello, everyone. This is going to be your online video lesson. It's going to be a little different. I'm going to pre-write a lot of the definitions out to kind of save time on the video. So you might have to pause it so that way you can write the definition in your notebook and the examples. But, follow along. This is all new territory. We can do this. Today, we're going to talk about lesson 5.1. So I know it seems weird we went to chapter 8, now we're going back to 5. But I like doing that better. I like knowing the trig and then getting involved in chapter 5, which is approximating areas using Riemann sums. So we've done two things in calculus. Calculus is really important for two things. It helps us, number one, find tangent lines to curves at a point. That's what we've been doing pretty much all up until this point. We know that derivative means slope, slope means derivative, and that's what we find the slope of those tangent lines at a particular point. The other thing it helps us do is find area under a curve, which can be really, really tricky. So you're going to want to write that down. And again, pause the video anytime. So this guy, this mathematician named Riemann, Bernard Riemann, he was a German mathematician, he decided to take a curve and he thought to himself, well, why don't I create rectangles in that curve? So we're going to start in this first picture. Let me move this up. With a right Riemann sum. So from A to B, the way you do a right Riemann sum is you start on the right. And you want to know how many rectangles do you want to create? 3, 4, it's up to you. So let's say we'll just do 4. So you would start on the right, go up to the graph, and then draw over and create one rectangle. Then go to the next mark and go up and over. And then go up, and again, keep going up to the graph, and we're always starting on the right here. And go over. And we'll do it again. Most of the time, we make equal intervals. But what he would do then is, to find the area under this curve, he would just find the area of each of the rectangles and add them together. Now what would happen is, though, for this one, that little bit over there is an overestimate. So let's try a left one then. The left one, we start on the left. And again, I think I'm going to create 4 rectangles. Use my same curve here. You start on the left, you go up to the graph and go over, make a rectangle. Do it again, go up to the graph, over. Up. What's happening now? I am underestimating. Very good. Okay. So I underestimate. This one might be my favorite one. I like the midpoint one. But we'll take my same curve here. And obviously, depending on if the curve is concave or concave, or if it's concaving up or concaving down. Almost said convex. But again, you have your rectangles, again, usually of equal width. To do the midpoint, you actually start in the middle of that rectangle and you go up to the graph. And then you draw your rectangle within that width. And do that again. And you keep going up to the graph from the middle. I should have drawn it like that. And then again, one more time. And this one's a little bit better of an approximation. Okay. But what is true is the more rectangles, and right now I only have 4, but the more rectangles, the better the approximation of the curve. And there's some cool applets that I could show you, but this is pretty much the general idea. The more rectangles, the better the curve, okay? Again, you can pause this anytime. So what does that mean? So let's take a definition for Riemann's sum. Over a closed continuous interval, AB, your area is equal to, this is sigma notation, the sum of, from k equals 1 to n, of f of x sub k delta x. Crazy notation. What does it mean? Okay, this is pretty much a function defined at k. This right here, delta x, we're going to become even more familiar with it. There's other formulas, but that is your width for the function. Okay, this is your height function defined at k. I should say height. And then this is your width. So again, why do we have this sum here? Because we're adding up all those rectangle areas together. Well, what if I made a limit of infinite amount of rectangles? Well, then I can have this definition for area under a curve of a function y equals f of x on a continuous closed interval a, b, where the area is equal to the limit as n approaches infinity of all these rectangles, like hundreds and hundreds and hundreds. As I create thousands and thousands of these infinite amount of rectangles, what I'm actually doing is a new type of math called the definite integral. This is the integral notation from a to b of a function f of x dx is equal to the limit as n approaches infinity of the Riemann sum. Okay, so this is all the notes for the beginning. Now we're going to practice some actual problems. And to do that, I hope you downloaded and looked at this worksheet, okay? And this is what we're going to be working on. And I'm just going to do a few of these together with you, and that'll be it, okay? So I'll start this in the next video. At least make sure you copy down all those notes.